Hi everyone, my name is Sergio Dorado-Rojas, a second-year Ph.D. student at Rensselaer Polytechnic Institute advised by Dr. Luigi Vanfretti. My poster is titled Data Generation for Deep Learning via Massive Simulation and is part of a project called DeepGrid, sponsored by NYPA and NYSERDA. Machine learning is the art of programming computers to learn from data. It has been successfully applied in domains where large-scale data happens. Power systems is not an exception, because we have thousands of millions of data being streamed from phasor measurement units, but also are capable of computing or generating synthetic data via simulations. So, in particular, we would like to ask ourselves whether deep learning, understood as machine learning based on neural networks, is capable to bring us from the data inputs that we have in the form of either measurements or simulation outputs to what we want, that are metrics in real time that tells us something about the condition of the system, in particular of our New York grid that is undergoing a green transformation. So it is natural to evaluate deep learning algorithms that bridge us from here to here. What is the main problem? That measurement data describes mostly normal operating conditions, but we need also traces or pictures of that abnormal operating conditions that we would like to detect via or quantify via the deep learning algorithm. So we need to generate the data synthetically via simulations. Our approach to generate data from simulations is first to constitute a database of power flows. Basically, we generate these power flows using the information published daily by NYSO. Then we have to construct contingency scenarios, meaning that we trip some lines of the system or take some generators off. Once we have power flows and contingencies, we associate them automatically to constitute a simulation scenario, but we find a problem. For that many number of power flows, we have too many scenarios, so we sample some of them via Monte Carlo randomization process, and then we pass a subset of physically meaningful scenarios to a power system simulation tool to perform a time domain simulation or a linearization. The latter is more important in our case since we would like to study small signal stability. So small signal is always associated with eigenvalues. So once we have the eigenvalues, we label them, and then we pass everything to a deep learning module so that we can train a method that after training and after being deployed, can give us a stability metric in real time. And based on that stability metric, we can evaluate how the system is behaving. To generate the power flows, we considered the effects of load forecasting as well. In this year, it was revealed after the first outbreak of COVID-19 started that our forecasting algorithms are not 100% perfect. So here in New York, for example, we see on the left the actual load, the most recent forecast called here best, and the oldest one for the same day called here worst, and we see here that there are huge errors on the forecast. So what we did was to incorporate the effects of forecast in the selection as power flow conditions that are valid. So in this way, the power flows that we generate consider not only the actual measurements or the trends of the loads in the New York grid, but also the errors due to forecasting. How did we generate the contingencies? So we constructed an ad hoc Monte Carlo approach based on the number of lines or the number of elements connecting different buses. That number in these equations is n. For this system, n is 20. So that being so, we have to select the number of lines being tripped because our method is a two-stage Monte Carlo method. So that number k is selected by a modified Poisson distribution. So that fixes k, and afterward, with k fixed, we go to this equation and compute all the possible scenarios with that number of lines being open and select 1. And that is how we incorporated or we selected contingencies. After generating that huge amount of data, we use it to train several machine learning and deep learning solutions. So how do we evaluate what model is the best? We have proposed this metric that takes into account not only the performance of the algorithm, but also how long does it take to perform to get a prediction. So here we see that, as expected, if we use the domain-specific rule, we get a 100 accurate classifier, meaning that our result is perfect. But at what price? So our computations are slow. If we maximize only performance for the machine learning solution, we would have selected this classifier that is the slowest one. So there should be a sweet spot between this minimizing this criteria and minimizing the performance, and that is achieved by a neural network. So how well does a neural network classify the different contingency scenarios? Here we have a graphical overview. We see that it labels or classifies everything that is unstable as unstable. That is the most important and critical requirement for this kind of module. And there are some mismatches here on this region, but they are not that serious. They are not that many, and misclassifying something critical as acceptable is not that bad in terms of a small signal stability. So that is it from my side, and I hope that you have got an overview of the things that we are doing at RPI. Thank you so much.